this is again our third lecture, Peter's mini course. Okay, right. So let's see. Last time we discussed a bit the abstractions and the resistance questions. So abstractions, resistance. Essentially, one of the facts that we saw was that this class of projective structures, the set of projective structures on a fixed Riemann surface. So next, I'm going to stick for now to the projective structures because the affine ones are not going to write P of X for this. I'm not that interested. They exist only on. Yes.
I have a question to the last time stuff, by the way. So you wrote there the Schrödinger equation.
Right.
So the potential Q.
Yes.
Is this the proper equation operator which appears in this construction of Projective and the solution of the inverse problem there, inverse scattering problem? You know the way they solve, because what we are doing, these Opers, they are just generalization of the picture.
Sure, yeah. I mean, of course, one has to understand mostly the SL2 case or the PGL2 case.
Yes.
The rest is essentially a bit of a twist with for a general group. I think that's the equation that shows up. Yes. I mean, there is a you can describe these structures as differential operators from what's that? K to the 1/2 to K to the 3/2 with a symbol that is invertible. So I think locally that's it. Yes.
That's it.
I think that's the thing. I haven't recently looked back at the so-called paper, but from what I remember, that's.
And does there exist the analog to the inverse scattering method there in these Opers? In the whole theory of Opers, does it appear some way? It has to appear. Because this is the proper way to find the solution to coordinate freeze, right? Just this very fundamental stuff. The algebraic geometry appeared, but it means that.
Right.
Yes.
I'm not sure. I haven't.
Because I checked papers where they trace the connection between Opers and the coordinate freeze. I didn't see this. I mean, precisely this inverse scattering transform, and this is the top of the science there. See.
Yeah, I have to think that's. I mean, there should be some.
There should be some place.
Yes. Interesting. Yeah.
That is the second point, maybe it's more philosophical. Yeah. There was a work which was famous at that time in the 80s. It appeared in 1981, 2, 3, 4. The famous Japanese school of Sato. So Sato invented his point of view from which all those integrable hierarchies of coordinate freeze and Potter, you may formalize them algebraically by means on a, if you consider an infinite dimensional Grassmannian.
Yes, the Sato Grassmannian, sure.
So is it related to the Opers?
So there is a couple of papers on, I think, David Benz-V, possibly Benz-V and Frankel. There is, yes, I mean, I know that this link has been at least partially explored. Yes. Yes.
So it's not subset of these Opers, of the theory of Opers. It is subset.
I mean, this is a so for a fixed curve. This is a finite dimensional vector space. So this is we essentially saw that. So there's nothing infinite dimensional here in this picture, right? This is an affine space that's modeled on the quadratic differentials. Right. So here, let's say we assume the genus is at least so that we don't have to worry. So I think there's this paper of one is Benz-V and Biswas on Zegel kernels, and Opers, and
Viscous.
Viscous, the individual viscous, yes. So he had a bunch related results actually. But then the viscous and Benz V was maybe 99 or so. So I know that the Vertex algebra guys of course use this viewpoint of the simple inverse magnets. I can look for a couple of more precise references. Yes, but I think that's. This was Benz V and Frank so we actually, this was had last month actually had a paper related to projective structures, but that was for a certain property of the space of projective structures. If you do them relatively, if you also move the curve, so we do it over the Teichmüller space, and there was discussing functions on this space. Actually, it turned out that there are no non-constant function. If the genus is greater than strictly bigger than 2, if you do the relative picture, there are no constant functions. Anyway, I mean there's the various aspects. Some of these are related to differential operators, and so yeah, I could look for some references for the link with the sacred presence and the subject as mine, yes. Right. So what else did we do? So we mentioned, I want to expand a little bit on this, that there is a theoretical map from this space P of X. So I'm going to write P of X for the space of projective structures on X to use the homology group H on X PGO2C. Right, so essentially the way you construct the map is, well, one structure here is an equivalence class of projective atlases, right? So if you have your alpha, Z alpha, your projective atlas, let's say P alpha beta are the transition functions, then you just send this to the respective class of these P alpha, right? So maybe I want to clarify this more or less. I mean, it's a familiar space to many of you probably, but still. So if we have maybe just a reminder, if G is just any group, it doesn't have to be just an abstract group, right? They don't need any extra structure. And if we have any couplet of X, right, you can look at how to define the first cohomology with coefficients in the group. So if the group is not abelian, right, you typically have a problem with defining the second cohomology, right? So we're just using C1. We could define the cochains, right? We could think of this CQ of U with coefficients in G to be just the maps, let's say maps P that take the Q plus 1-fold intersection to each. There is potential of confusion here. So I'm thinking of this as an element in the nerve of the couplet. Right? So on each intersection, I'm assigning an element of the group. Right? This is just so that you should label these in some way. Right? So if you want, these are just some functions, P alpha 0, Q. I mean, these are functions, but these are constant functions, right? think of them as functions. So it's just one element of the group for each q-fold intersection. Right? So we just need C1 here, right? So on each double intersection, we assign an element of the group. The co-cycles here, right, are the ones that satisfy the co-cycle condition, but just keeping track of the order, right? These are P alpha beta, such that P alpha beta, P beta gamma is P alpha gamma, right? And the H1 is the quotient. Again, these are constant maps. So if you want. So our H1, well, if we're computing it on a cover, this is just the Z1 mod the equivalence where you identify these with, let's say, theta alpha, P alpha beta, inverse, right? Where this connection, the theta alpha is a zero chain. So you again, we're just keeping track of the order. So you try to mimic the definition in the abelian case, right? And then you get rid of the curve by taking the limit, you pass it to the finals. Right? So G is the limit over the different curves. So that's exactly the kind of data we're getting here. Right? In the atlas, the projective atlas, the transition functions are, so the coefficients of this, the coefficients of these P alpha betas are fractional linear transformations. The coefficient, these four numbers, the class of them determines a one co-cycle on each double intersection. Okay, so that's.
Did you say this canonical map is Lagrangian or something?
So I haven't yet. I mean, at the end of the day, okay, I'm going to discuss a bit more. It's not even clear that this map is actually it's 1-to-1, and actually the images of Lagrangian, we haven't put yet the structure, but yes, this you can think of this as the space of, let's say, you can think of it as flat P1 bundles on X, or you can think of this as PGL2 local systems. There are a number of ways in which you can put a symplectic structure in this space, but yes, there's a canonical symplectic structure, and the image will be Lagrangian, yes. I'll try to argue to explain a little bit why this map is actually 1-to-1. It is not 1-to-1 if you just look at the topological surface. In fact, in some form, Poincaré had a proof that this map is 1-to-1, but he was thinking of this space as a representation per additive. I'll get to this. And just one more maybe notational point. Sometimes we need to look at an kind of associated bundle. So if we have let's say S is some, you can have a topological version or an analytic version. So if this is either a topological space or the variant would be, let's say, complex manifold. You could try to look at complex spaces if you want, on which G acts. G acts, okay, whatever the group is. I mean, for the moment, this is for an arbitrary abstract group, right? And let's say if you're looking at the topological case, we'll ask if it acts by homomorphisms. If we're looking at the complex case, G acts complex analytically. Then if we have one of these classes, if we have one of the classes in H1, we can look at the associated bundle with fiber S. So we'll write, so given, so if we have this space and P is a class in H1 XG, we'll write either C of P as there's no good standard notation, or respectively all RPS for the sheaf of sections of the associated bundle with fiber S. So again, what does this mean locally, right? Associated bundle. Yes. So so the way you build this, I mean, the sections of this sheaf are, you look at local maps from X into S, right? Or let's say, just as a idea, so a section here of this sheaf, let's say gamma, whatever X. Let's say if we're looking at, we're looking at the homomorphic case. So let's say, yes would be, so they will be given by some maps U alpha into whatever this space is. And they will be glued by the same, they will be glued by the phi alphas, right? By the phi alphabet. And so these will be homomorphic. If we're doing the continuous case, there will be continuous maps, and they're glued by the cross cycle of phi. For P in the intersection. Essentially, you take this type of data and you sheafify to build this sheaf. So we need a couple of examples in the proof of the next theorem. So maybe one case that would have is, let's say, S would be just C2. S would be C2, and the group would be G02C. Right? So then this bundle, this O phi S, right, would be the sheaf of sections of a rank 2, of a flat rank 2 vector bundle. And the other example that would show up would be S would be just P1, and G will be PGO2. And so this whole P, this would be a flat projective bundle. So, just fixing the notation. By the way, okay, so there are some, I'll attempt actually to give a couple of answers to this question. Last time, how do we characterize the image of this map? I mean, there is a nice answer from maybe from about 15 years ago, which characterizes the image by Martin. But there is a sort of homological description which is a bit less, which in terms of this case H1. So I would need just a final bit of notation. If I'm looking at sections that are Walker homomorphisms or complex analytic homomorphisms, we'll put a subscript 0. So also write gamma 0. We could do this on any sufficiently nice topological space, right? I don't need anything about X being Kalima surface, but that would be the case. So we're going to have gamma 0 inside gamma. This PS, and gamma 0 over PS inside gamma. For the sections that are local sections which are local homomorphisms or complex analytic so one criterion when the class H1 actually comes from a projective structure is that we have a non-zero section here. So that's one thing that I wanted to mention. It's not explicit, but it's. By the way, this space is sometimes called this. People would call it the space of coordinate sections of the class phi. So this gamma 0 is sometimes called the space of coordinate sections. Why is this terminology? And we have the cohomology class in H1, and we have a space on which the group acts. So here some sections of the associated bundle, but these sections as maps from opens in the curve to whatever the final is, for us it will be P1, are local homomorphism. So this is a kind of, you can use the sections as a kind of coordinates on your curve. So these are, that's why you think of these as coordinate sections of the class. So then the observation is that a class phi in H1 X PGL2 C is the class of projective structure under the map that we discussed. If and only if, essentially this space is not empty. If and only if gamma 0 X O let's say P1 is non-empty. In other words, if and only if you have a section, a coordinate section of this associated bundle, which is a local homomorphism. This kind of coordinate section. It's easy alpha in this space. So, right? Why? I mean, what are we saying? That if we have such a class with respect to a certain cover, we will be using the phi alpha betas to be the compositions z alpha after z beta inverse, conversely, if this class comes from a projective structure, again, you can pick a projective atlas, and then these z alphas will be the local coordinates for that projective structure. So this is a kind of characterization. It's not explicit in any way, but saying you with the class, right? This is some this H class in H1 corresponds to some P1 bundle, some root surface over the curve, right? So it's a flat P1 bundle with transitions with transition function that's a constant. So if I can pick a local section, so if I pick a global section which is locally a complex analytic homomorphism, then that section, that phi comes, so is the class of the projective structure. So is this making any sense?
Just checking my understanding. So the difference of gamma and gamma zero is like one has so originally it has a flat connection. Now we get the flat connection. Just consider the section.
So the gamma zero is a subspace. So in which you have sections, so it's a global section, but so locally each of these is a map from an open to whatever the standard fiber is. And I want this map to be a local homomorphism. So for the case of P1, these are local maps from opens in the curve to P1, and I want these to be complex analytic homomorphisms.
So on a higher dimensional variety, you don't need the fiber to have the dimension, at least the dimension of the variety, otherwise.
Yes. Right. Sure.
And for a curve,
right.
As long as the fiber is positive dimensional.
Right. By the way, yes, of course, one can consider, you can make sense of projective structures on a higher dimensional. The theory is slightly different, but you could be asking that. You could be, anyway, I mean.
I just mean that there this condition becomes more somehow.
Yes.
You see that we have some condition.
At least that dimension.
And some other things that could happen in trees.
Okay, so in the example S equal to C2, what are gamma and zero and gamma?
For gamma zero, so I won't have, I will be having, so here the fiber is C2, so I don't have a chance of having such a gamma zero will be dead. That's essentially, right? If my standard, the base is one-dimensional, so this S is C2, right? P1 is one-dimensional, and here I don't have even the chance. This gamma zero will be zero, I'm saying.
Okay.
Yes.
But S is the fiber. S is the fiber, right?
Right. This is the fiber. Yeah, I want to have local works between the base this in the fiber. So this, I need at least the dimensions to have a chance. I need the dimensions to be the same, but they're smaller. So we have some description of this. Now there is a short exact sequence. We have the short exact sequence of plus minus the identity going to SO2, C going to BGO2C. I mean, I imagine 0 for the 0. Let's say mu for the quotient, that BGO2 is the same as PSO2, right? So this gives a map on H1, which uses, I'm still going to write it as a map, mu, okay, mu on H1 SL2 to H1 BL2. So, let's see. Take the class and reduce it 1%. So the lemma, so I want to formulate the lemma, which is a key ingredient in showing that the map from projective structures to H1 is injected. So actually every class that comes from projective structure can be lifted to SL2. That's the first part of the lemma.
Peter, I'm confused. So for the gamma, do we get the flat section or the notation gamma x? Or do we get to the flat section or holomorphic section?
Wait, there would be, so the bundle is the flat bundle, but these would be all sections. To be all sections.
Okay, so the notation gamma, actually you forget about the flat structure. You just keep track of the.
The sheaf that you get using the flat structure, and you build the sheaf using the standard fiber and the class in H1.
Yeah.
So the flat structure is in the way, I never wrote this carefully how you describe the sheaf, but I wrote essentially what the local section looks like, right? And then you glue the local sections by the data of the feed. So the flat structure is is built into the definition of this.
Okay.
Yeah. Here is this somewhat technical lemma which has a couple of interesting ideas here. So if you take a section in PGO2, H1 PGO2, so if D is the class of the projective structure, then there is a class in H1 SL2. There exists, let's go with T in H1 X SL2, such that first of all mu of T is class phi. That's the first part. So the class lifts, and then the second part is if we pick up on these coordinate sections. So if it's alpha, I'll just type gamma 0 for this whole. Actually, let me write it. So let me not be lazy. Gamma 0 in all FP1. If this is this coordinate section corresponding to phi. Then we can describe this data more kind of clearly. Then there exists a C in H1 X C star. And a couple of, so a global section H with components H1 alpha, H2 alpha in gamma of phi with O phi C2. So it's O I need more space. I'll need more space. In so it's a section of X with O of C times T C2. Such that the Z alphas are the ratios of this. Okay, let's see what is. So there are two parts to the statement. So the first part is you pick a class of H1 P0 So it corresponds to some flat P1 bundle. This class or in principle may not come from projective structure. We're saying if it does come from a projective structure, then first of all it lifts to a class in SL2. So there is a class in H1 SL2, so that we are DC. And second, in that case, right, this phi could have some coordinate class. There is some section of this P1 bundle associated to the cocycle. So if you pick this coordinate section, I should say of phi, right? Then you can find a flatline bundle, so H1 C star, and a section of the rank 2 bundle, which corresponds to T twisted by XC, so that the Z is the ratio of the two sections, right? So essentially we're finding a rank 2 bundle, which is we're trying to deprojectivize. I'm trying to write the P1 bundle as a projectivization of a rank 2 bundle. So we're looking at the PGL2 class, we lift it, then up to canceling with a flatline bundle, this class CT gives a rank 2 bundle C2. There's a global sections here, and our Z is the ratio of the two sections. So we can write the coordinate section as a ratio of two sections of this vector bundle of rank 2. So is the statement somewhat making sense? Just a comment for who just came, right? So we are writing this O of PP1, for example. So as for the sections, for the bundle, for the sections of the associated bundle with phi 1, let's say P1, and determined by the homology class P. So let me maybe outline this. We outline the argument. So first of all, we'll try to lift, right? So we're starting with the projective structure. Let's say we pick a projective atlas. So let's say U alpha, P alpha is a projective atlas for this class. So so pick a, so these are Z hours, and Z hours. We have our class phi alpha beta. These phi alpha beta are in PGO2. See? Now you can lift them. So this is in C1. So we pick a cover that computes the mortgage. I pick a good cover if you want. Now you can lift on the nose. You can lift each of the phi alpha betas to the SO2. So we pick this phi alpha beta in SO2C. Right. So that phi alpha beta is this. Right? The mu here is the quotient path from SO2 to PGO2. So again, these are constant matrices. Let's say one rank this matrix. It has some components, right? A, B, C, D. In SO2, right? So in other words, again, practically, this means that on the overlap, my coordinates are included by this SO2 matrix, right? Z beta plus B alpha beta, C alpha beta, Z beta plus D alpha beta, whatever, right? We pick represent the transformation by SO2 matrix. Now, notice that the canonical bundle, right, will be given by the squares of these denominators. So the canonical bundle with respect to this cover, right, has transition functions. Let's say kappa alpha beta. Well, again, the derivatives of dz beta dz alpha, so this denominator comes in squared. So we're trying to construct a lift, right? We're trying to lift the class to an SO2 class. And essentially we can do it on each double overlap. The question is, to patch them. The patching is the question. So here is how we can do it. Just pick, let's say G is the genus of the curve, pick G minus 1 points. Pick points 1, PG minus 1, next. Right, so PG genus. Right? And look at the line bundle, all of 2p1 plus 2p2, etc. So instead, what am I going to call it? Z to be all of 2p1, so 2 times pg. And so this is a line bundle of the same degree as the canonical. So, at the degree of k, so this line bundle is going to differ from k by a bundle of degree 0, right? So, zeta is the canonical tensor with some line bundle eta, right? Some degree 0 line bundle. 0. Now, sorry. A degree 0 line bundle is always flat. You can always think of it as every degree 0 line bundle needs a flat connection if you want, or it can be given by constant transition functions, right? So eta is in h1x C star. Right? This is the C star is sitting inside the O star, right? So give something like this. So now this is we can pick a global section of this guy has some global section. Pick a global section that vanishes at this point. Pick a global section such that zeta is all of that global section. So pick again abusing the letter G, but pick G. Yeah, the edges of X. Sorry for this. Pick G in H0 of zeta, so that we can write zeta as all of that section, right? This is all of 2p1. So pick a homomorphic section that vanishes at these points. So what happens on the overlaps? On the overlaps, the G alphas are going to be denoted by these numbers times some constants, right? Because zeta is the canonical tensor with some line bundle with constant transition functions. So on U alpha beta, putting the intersection, I have that G alpha is this vector there. C alpha beta is a vector plus the alpha beta squared times some constants which are the transition functions of eta. Alpha beta in C star. In the transition functions of the line bundle. Am I making sense so far? So I picked, I lifted the element of PGL2 that represents the structure to a matrix in SL2. So I have an SL2 transformation changing from one coordinate to the other. With this atlas, I'm using the projective atlas coming from the class phi, I mean representing the class phi. But on this atlas, the canonical bundle is moved by these transition functions. Now we pick, essentially we pick a homomorphic section. This is a G beta, there's a G beta. Right? We pick a homomorphic section of the bundle of Z. So pick a bunch of points. This bundle has the same degree as the canonical, so it differs from it by degree 0 bundle. So that degree 0 bundle has constant transition functions. Right. And then on each open we pick a root of this. So on call this function. I want to call it h alpha, but they're only going to be in the statement at the level there are h1 and h2, and this is going to be h2 sub alpha. Now, why does this exist? We may need to pass through a refinement for this word, but the point is G is vanishing at an even number of points. I think there is this exercise in complex analysis. If you have on a simply connected set, if you have a function that vanishes at an even number of points, you can pick the root, the square root of that. So we're using that my function G has even zeros of even order. So that these H2s, they grew by, not by the squares at least, but we're getting rid of the square here. Right? So H2, there'll be some constants that will be the respective roots of eta alpha, so we can choose the roots compatibility. So H alpha is C alpha beta is beta plus D alpha beta. Again, times some other constants C. And these constants will return in the flat bundle that we see in the statement of the lemma. Times H. So this is H. H2 sub alpha. H2 sub beta. Okay. So this is the H2, and H1 would be just Z times, so H1 of alpha is Z alpha H2 alpha. So we are building this relation that the local, the coordinate representative of the cocycle should be a ratio of two functions. We're building it into the definition of the H1 and the H2. So, and so what do we get so far? So we get that this vector H1, H2 transforms with the matrix T twisted by C, right? Thus this vector H1 alpha H2 alpha transforms like, I'm not going to copy the matrix, it's the same matrix, the alpha beta H1 beta H2 beta times these coefficients C. So this is this T alpha beta was a matrix in SL2. Okay, we're multiplying it by some Hodge factor, which would make it in general in GL2. But getting rid of, by not further normalizing, you will make it again into SL2. So GL2. So dividing by the determinant, we get so somehow that was the idea, right? So there were two things in the lemma. We lift the class, and then we can find a section of this rank 2 bundle, which is associated with xi times t, where this t is the limit. And our coordinate functions are the ratios of these two sections. Let's see. Let's be here. All right. So this is again. This is a kind of it's a kind of technical argument, but it's a useful statement because it gives us almost immediately a very non-trivial result, which is that the map on projective structures page 1 is injective. The canonical map, I didn't give it a name, sorry for this, but from Px to H1 x T0 to C is injective. So just again as a remark, so it's actually a theorem of Poincaré who described it in different form. He thought of this space as being the space of representations of phi 1. He showed, so Poincaré showed it, but with a sort of a version of this theorem. So this was known. As a map, projective structures to forms phi 1x T0. So I think this was 1884 on the groups of linear differential equations. Poincaré has some paper on the groups of linear differential equations in which essentially he proves that the monodromy of the projective structure, the monodromy map of the projective structure for a fixed Riemann surface is an injective map. So it follows almost immediately from the left. So let me maybe just outline the argument, and then I'll maybe comment more on the other viewpoint, on the topological viewpoint. So let's say we have two projective structures that go to the same class. Again, we can assume that we've taken the same ethos for both of them, just the functions, the same cover for both of them, but the functions are different. So let's say, so suppose we have, let's say, U alpha, Z alpha, and let's say U alpha, W alpha. So these are projective atlases for two different, well, possibly different, for two projective structures. And to assume that they determine the same class in H1. So determining the same the alpha beta, same P in H1. Again, we may assume that we've already chosen the color compatibly, so this phi is represented by both ratios of the phi of the z's and the ratios of the w, right? So I can write either as z alpha z beta inverse, or let me just. So this is the class. I can think of it in PGL2, but by the previous lemma we can lift it, right? So this class lifts. So we apply the lemma to each of the two. There will be some lift that comes for the z's, and there will be some lift that comes for the w's. I also pick, let's say t in H1 x SO2. So this is mu t is phi, right? So class of G alpha beta is in SO2. And what do we know? There will be these x's and the ethers. So let's say xc also xc eta flat bundles. So each of the respective Gauss-Seidels representations, xc alpha beta, eta alpha beta. And there will be the two h's that we have. Again, for each of the projective structures. I'm going to call them GH. So H, let me make sure I label them compatibly. So G is G1 alpha, G2 alpha. And so this is a section of the associated bundle. So zero of what is that? CT C2. I need more space. Sorry. And this is in my gamma 0. So gamma O CT C2. H is in the H1 alpha, so H1 alpha, H2 alpha, in gamma XO eta T C2. Right, so up to a twist by degree 0 line bundle, there is an associated rank 2 bundle whose it's associated to either C times T or eta times T. And the Z's are the ratios of the G's, and the W's are the ratios of the H's. So we apply the lemma to each of the projective structures. So that Z alpha is the ratios, let's say G1 alpha, G2 alpha, and W alpha is the ratio of these two sections. Right? And now what happens? We can think of the we'll be trying to show that these two are linearly dependent everywhere, right? So if you look at the matrix with columns, these two vectors, so set say F alpha is this matrix. G1 alpha, G2 alpha, H1 alpha, H2 alpha. Okay. So each of these is a section of some vector bundle. It's a global section of the global section. These are the local representations. So on each of the opers, I can look at this matrix. Now, what do we know about the gluing of it? Right? So it's a matrix with entries for morphic functions. We know that they get glued by T, well, times C times theta, right? So F alpha is, so on the overlaps, on U alpha beta, F alpha is whatever the matrix T alpha beta is, times this diagonal matrix with C alpha beta 0 just beta alpha beta. Right. So the sections of G transform with the cosine of C times T, the sections H transform with the cosine of theta times T. So we look at the corresponding 2 by 2 matrix. Now it gets glued by these transition functions. Now, looking at the determinant, the determinant, so T is in SL2, while these two are degree 0 sections. So degree 0 line bundles, right? So determinant of alpha is C alpha beta, beta alpha beta, times the determinant of beta, right? Because T alpha beta is in SL2. So this means that these determinants, they glue to a global section of the line bundle C tensor eta, which is a degree 0 line bundle. This connection here is an element of H0 C tensor eta. This is a degree 0 line bundle. So this means either it either has to vanish nowhere or it has to vanish identically. But we know that it vanishes at G minus 1 points, so it actually vanishes identically. So either alpha is identically 0 alpha, or it is nowhere vanishing. But it must be this case. We are in this case because the sections of C vanish at G minus 1 points. So the G alphas, I mean these vanish. So one of the columns of my matrix vanishes at G minus 1 points. So this means that the determinant vanishes somewhere, so it has to vanish everywhere. Right? G alpha vanish at G minus 1 points. So these are everywhere dependent. Right? These two, the determinant is 0, so the two laws are everywhere dependent. So the coordinates are everywhere equal. So G and H. So G and H are everywhere. Which means Z is double so we have, so in this atlas, the two coordinate functions, the two flat coordinates are actually equal. Right? So that's the idea. So we started with two projective structures. We picked sections of these associated rank 2 bundles. We applied the lemma to each of them. There's a single lift to SL2, and these are twists by two different degrees line bundles, and then we just checked what happens with the determinant, and I saw that the determinant has to be everywhere 0. So, so the two flat coordinates are the same. Took me more.
Okay, the mean Z alpha and the W alpha differ by a linear fraction or linear transformation?
I mean, these are two vectors that are linearly dependent, so one is a multiple of the other. But so when so when I take the ratio, right? Yeah. So when I take the ratio would be actually dead equal.
I don't think they are equal, but differ by a fraction or linear transformation.
I write it explicitly because it's so
I mean,
simple that
G alpha
times H is equal to the cross products are equal. So it's the determinant being equal to 0 means that the cross product.
Sure.
They are actually equal.
They're equal, right? A vector, for two vectors, linear independence is the same as being multiples.
Yeah.
So this vector is a lambda times this vector. So when I take the ratios, lambda cancel. So it's not just a projective transformation, it's dead equal. Okay. So maybe just a couple of so a couple of remarks. So first of all, this choice, there's something that probably I should have said that a bit earlier, but people have started suspecting it, I guess. So this choice of projective atlas, right? So the choice of projective atlas, let's say U alpha, Z alpha, right? Actually gives us, or corresponds to having a map to P1, or onto a velomorphic function, as we call it, again Z, from the universal coverage to P1, right? So sometimes you call this the developing map of your projective structure. And what properties does, so the universal cover is the upper half plane, right? Here. And what do we know about this? First of all, dz, so this melodic function differential is never 0, right? On x tilde. And second, if we act on x tilde by the fundamental group, the values get conjugate, right? So z of, let's say, g of some u is some low g z of u, right? For u in the universal component. Well, rho is some representation of pi 1, right? Rho representation from pi 1 into PGL2. this representation is not uniquely determined, it's determined after conjugation. Right? You can pick generators of the fundamental group, see where each of these sends your, how each of these acts. You can get a conjugate representation that would, also work. So determining after conjugation. So having a projective structure, again, you can lift everything to the universal cover. So it's good giving a single monomorphic function. So this is another way of packaging the extra data of this equivalence class projective atlases. We have a monomorphic function for the universal cover that's has non-vanishing differential and transforms with a certain representation. Right?
It doesn't have a G inverse somewhere when it acts on the argument. Usually you act on functions by
yes, it should be you're saying
Z of G inverse you say, or
yes, sure, yes. That's you're getting a right action. I mean, yeah, I should be having if I'm thinking of X tilde as a principal pi 1 bundle, I should have it act on the right. So yeah, I should have the right action. Yeah. So from this data, actually, you can build yourself a principal bundle. Right? As always, actually, this again is a standard construction. So from such data, we get the P1 bundle. Or if you want, again, a root surface, right? Right? What's the P1 bundle, right? You take X tilde plus P1 and you mod out by the P1 edge. Right? So you take the trivial bundle with fiber P1 on the universal cover, and you pass to the quotient using the representation. So you have the P1 bundle. You actually have a section. Where is the section coming from? Let's say sigma. The section sigma of this. The section is essentially the image of the. Here you have the graph of this function. So the graph descends to a section, right? So sigma of x is the global section, right? So this is the class of the graph. I'm writing the image in the quotient, right? So the graph here is in x to the x, right? So maybe a kind of picture would be right, we have x tilde plus q1, right? And we have your graph of z, right? The graph of this function from x tilde to p1, and then you descend this to a kind of p1 bundle. With could it use a different color, but yeah, with a section here. Right. This is the H. Right. So we have again the projective atlas is the same thing as this monomorphic function. This monomorphic function, and so some of the representation data we can glue up the P1 bundle from the section, from the graph we get a section, and actually the section here has a non-vanishing derivative, right? So, so actually here on the product, on x tilde equals P1, we also have the horizontal foliation, and it descends. So, so the horizontal foliation here descends to a horizontal foliation on the root surface. So we have foliation that is transversal to the fibers. Here, it descends to horizontal foliation on x tilde equals P1, descends, and being a bit sketchy, right? So descends to the quotient. So we have our P1 bundle with a section, right, and a connection. The section is transversal. To the section. So that should be, we have just a couple of additional remarks, right? So this is another way of seeing the same data. We have the class in PGL H1 PGL1, which gives us a P1 bundle. Okay, here's how you think of the P1 bundle, sort of geometrically. Now, from this viewpoint, we see that maybe a second remark is we see that we have a canonical map from projective structures on X to the space of representations modular conjugation to home phi1 x PGL2 not PGL2. Right? Now, again, as I mentioned also last time, this is affine. This is affine algebraic variety actually, right? Because if you have generators A1, AG, B1, BG for the fundamental group, right? We can get the representations by looking at matrices A1, AG, B1, BG that satisfy a relation, and the relation is the product of the commutators. Equals the idea, okay? So you can get so this representation variety, right? It is a subset. This lives. It's a subset of PGL2 plus PGL2. 2G times. And you can look at matrices in PGL2 that satisfy the final corrections of phi 1, and then you mod this out by binary conjugation. So this is an affine variety. It depends only on the topology. This doesn't see the complex structure. It's the complex structure of this set is independent of the complex structure on X. It just sees the topology.
Is it just this quotient or is it some GIT quotient? Do you have to remove something?
Depends what, yes, typically, so if you want to get the good stuff, I mean, if you want to get it to the right way, you have to take the GIT quotient or remove the, look at the reducible representations. So typically, actually, right, indeed. So you look at points that are, you look at closures of orbits as your points, but yeah.
After excluding everything.
I mean, if you exclude the bad stuff, you will take just the quotient. But this depends on, okay, what
maybe it's too much. First you have to exclude all orbits that close at zero, and then you take equivalence by orbit closure.
Restrict to regular, I guess, you restrict to regular orbits, then you would have a regular representative in each orbit. But typically you need to take the whole, everybody with the same, I mean, there's an equivalence class of, but the usual adjoint quotient also. So it's the point is an affine algebraic variety that just depends, it just sees the topology on X. One can show that this, as I said, is in bijection with P1, right? And sorry, in bijection with H1. So our H1 PGO2 bijection with this representation variety. Now, just as a caution, if we, so this depends only on the topology. If we take here the topological surface, the map stops being injected. So just a caution. If let's say sigma is the topological surface underlying X, then the map projective structures on sigma to the respective representation. And this is the monodromy representation of the projective structure. Right? R1x PGO2 not PGO2. Then this map is actually not only, it's actually a local diffeomorphism. It's a local diffeomorphism. So this is the theorem of Hayhow, I think in 75. So if you let the complex structure there, just looking at the topological space, you get a map here that is a local diffeomorphism. Actually, I think it's a counterexample to many. It's a counterexample to many natural expectations. So it's a local diffeomorphism, but it's not a covering map. So so the two have the same dimensions, right? This has the two spaces are the same dimension. This is the map. It's a local diffeomorphism from one to the other. You could think of this slightly differently. So instead of considering the topological surface, you could think of the family of projective structures over a tight mirror space, or over the modular space, but you have to be careful with the stacking issues. So if you let's say so you can improve the statement that's a theorem of Hubbard. So in fact, if we consider let's say the everything relative, so if we consider relative projective structures, so we have to say what is the family of projective structures over, let's say, over a disk or over some if I have a family of curves, what's the family of projective structures over this family of curves? So you can build a space P over the space of X. So if I have some class of some curve here, right, the fibers, the respective space of projective structures. This has dimension 3g minus 3. The fibers have dimension 3g minus 3. So this has a natural complex analytic structure variety of dimensions 6g minus 6. And you can look at the monodromy map from P2 representation variety. So then the map P from home is pi 1x PG02, not PG02, is a complex analytic walk-away from morphism. Is a complex analytic homomorphism, right? This is I mean, why I have to show that this space has a natural, the space of all projective structures over all curves, right? The relative version. So over each point in triangular space, you look at those corresponding space of projective structures. They glue to a family. And this family has a natural structure of a complex analytic space. So the monodromy map is a complex analytic walk-away homomorphism. This is Hubbard. So it's a strengthened version of Hayhouse theorem. Hubbard 81. So the final thing I write is the answer to another question that appeared last time. Final result. We have the theorem of Gao, Kapovich, Martin from the year 2000, which determine exactly which representations arise as monodromies of projective structures. So they say that the representation, so an element in form pi 1 sigma PGO2 is the monodromy of a projective structure. If and only if, first of all, it lifts to SL2. Right? We have two classes, right? There will be the ones that lift and the ones that don't lift. So it has to be the one that lifts to SL2. And it is not in the affine group. So up to conjugation, rho is not in the affine group. So the group of affine transformations. And rho is not in PSU. And so I think this was been some conjecture in the topology that's been open for a number of years. People had a topological argument why, if you have these conditions, you cannot be a monodromy of projective structure. So why you cannot be an affine in the group of affine transformation or in the PSU, and Kapovich-Martin showed that actually that's sufficient. So again, it's a bit indirect, but as long as you cannot be conjugated to an element of the affine group or in PSU, and you lift SL2, you are a monodromy of projective structure. So this is kind of more explicit answer to this question from last time. So I'll stop here one over time, but it starts a bit late.
We started late, so it's okay.
So
technically, it's only 5 minutes.
Okay.
So it's good. Okay, thank you. Now we can ask freely questions.
Do we know that this characteristic variety has how many connected components? Is it connected?
It's connected, right? It's connected. It is normal. It is connected. I mean, you know, the topological class. The topological class of a line bundle. I mean, a line bundle is always a flat bundle is always topologically trivial. So there's only one. Essentially, there's only one connected component.
That's for line bundle.
No, but no, I mean the line bundles. You have your G bundles characterized by pi 1 of the structure group, whatever. But it is connected. It's the moduli space of local systems. It's another way of thinking of this. It's the realm space. I mean, this what is we can think of an object here as a pair of a principal, let's say PGO2 bundle and the connection. Now you have a map from this space to BUM G. You can forget the connection map to the moduli of bundles, and you're always going to land in the connected component that contains topologically trivial bundles. Right? So think of a flat bundle as a pair of a bundle plus connection. Forget the connection, so this space maps to a dense open. This space maps to the moduli of bundles. There's a rational map because not every topologically trivial bundle needs a connection. But so it's just connected. It's normal. I mean, it's typically it is singular. Again.
So if that is true, back to the lemma you have before, the lemma says the class in the class. I mean the SL2 to PGL2 map.
Yes.
If you have a lift, right?
Yes.
So the obstruction.
Sorry. For PGL2. Sure. For PGL2, sorry.
If you
I mean, you're right. I'm saying something slightly. We're working with PGL, not with.
I would believe there are.
Sure. So we'll have to. I mean, there are representations. There are representations that do not lift SL2. Sure. I'm saying something. Yeah, this has to have two connected components. Sure. Okay. Because the representations that don't lift. You can look at some kind of analog of the long exact sequence that comes from the short exact sequence of. You have a bit. So for that sequence, you're right. We'll have two connected components because we'll have the map from the center to SL2 to PGL2, and there will be some bit of the long exact sequence of the H1.
Yeah.
So right, there is another component, the ones that don't lift. So what I said was what was for SL2, right? That I can have if I have a rank 2 vector bundle, I would have a forgetful map to the modular bundles. But here, it seems that I would have to connect to components. Right, sure. My bad.
Okay. And yeah, in that lemma, it leads to a SL2 bundle. So this is the jet bundle of k to the power minus 1 half.
This is the frame bundle of that. Again, that's determined after twisting with the line bundle. Yeah, I'll come to this next time. Yes, you can. These are SL2 bundles, so you have to take that first jet bundle and look at the principal bundle that corresponds to it. Look at all the it's the frame bundle of that. It's the frame bundle of J1 k minus a half. Okay. Or you can twist it, of course. So there are many different vector bundles with the same projectization. And you can always twist by a line bundle and get the same class in PGL. But if you want to lift it to SL2, it's J1 k minus a half.
Yeah. So the choice of lift is the same as choice of the square root of the canonical bundle, or that's the same as the spin structure.
So here the statement is, the bundle is not going to move when we look at the pairs. So the class phi is going to correspond to let's say the bundle, the flag. There's a bundle. So we have a P1 bundle with a section, or a rank 2 bundle with a sub bundle, and D. Just the connection D is going to move. We are going to we have different lifts because of the different choices in this section.
I just wonder, once it would be nice to have a dictionary, of course, at least for me, to know how is this classical case, regulatories and all that stuff related and embedded in this generalization. For example, say projective
This is not
structures.
just a generalization. This is in a way that the PG. Actually, this stuff is clear. From this point on, I've set that in a way that now the generalization will become clear. But this is still the classical, meaning PGL2.
Yeah. Okay. So where is now just the projective structures, the Sturm-Liouville, or the Schrödinger operator, right?
Right.
Now we have the Baker functions there, the tau function, the Baker functions, and the theta functions, which are very, the fundamental stuff there. So I wonder where they appear now. They have to appear somewhere here. The Baker functions, these are the eigenfunctions. So what is the meaning of an eigenfunction for a projective structure, for example? So this is really the deep science which goes, this was the regulatory, power lattice, and all that business, which is.
So this space, when you start moving the curve, this is a kind of affine bundle, which is a twisted version of the cotangent rectangular. It has certain smooth sections that are not working, that are linked to projectivization, to pairs projectivization, and so on. So somewhere there should be maybe some lift to tau functions, something.
PGL2, that's it, that's the case.
That's it, yes. Very nice question. No, because there's a dictionary with the differential operators, but how do we see them in this picture? By the way, there is Yeah, there was a work of Opers, and this was maybe from a couple of years ago, where there might be something about this, but I'm
This has to be older.
this has to be, yeah,
It was 30 years ago.
Sure, yeah. This has to be,
30 years old. Maybe it's Dreamfeld, still Dreamfeld, so who they had described. I mean, Dreamfeld, those who worked.
I mean, they did, of course,
He published a paper in 2005, Dreamfeld.
but,
Some 20 years after everything happened, more or less. Yeah, they have Baylissen and Dreamfeld. They published a paper. They say we provide algebraic setting of
Right.
which happened 20 years ago. Now it's still 20 years after the paper. Baylissen and Dreamfeld.
and they published it 20 years ago, but it was back on 30 years ago.
Yeah.
I guess. I mean, they had it before that.
I found the reference, by the way, in the meanwhile. It was Siegel and Wilson. They published a paper in 1985 which shows how Dreamfeld-Sokolov stuff and the stuff at Sato correspond. More or less, yes.
So paper by whom?
Siegel.
Siegel, yeah, sure, I see.
Siegel and Wilson.
I see.
And Wilson, and they discuss about it. It's very nice description. But still the big problem in the whole area remains. I mean, okay, this is one, I would say, gives the framework for generalization. But the multidimensional stuff in coordinate freeze in Polar lattice is missing. This is the big job. Absolutely, you may say there's nothing there. After so many years, so many attempts.
You know, we can look at projective structures on higher dimensional varieties. That's, you can look for networks where you can group by automorphisms of PM. And no, that stuff, there you can say something, but yes.
So that's my curiosity in the stuff. Is it possible to find the germs of some multidimensional?
Sure, yes, I mean, some part of the tau functions business should be visible here.
Because physically, there are solitons, physically. They find them experimentally and things like that. But there is no such theory. I mean, there is nothing like what happened in the one-dimensional coordinate freeze and Tolelettis and Science-Gordon. So maybe algebra will give the right way, the correct approach to the problem. Some smart algebra.
Yeah, I'll need to look at this. There was something by Opers, and this was on projective structures and links to differential operators, and the quantum groups, but this is, I mean, it has to be here. It's packaged in some way that's not obvious.
If there are no more questions, I think we can thank Peter. And the next session will be on